Welcome back. Our previous video introduced generalizations away from the Bayesian approach and complications. And we also introduced a specific case of Bayesian learning models called the Kalman filter that's used in a variety of non-economics contexts. And in today's video, I want to cover a generalization of the Bayesian approach that we discussed earlier. And in particular, the generalization is to a vector-valued learning model, or a multidimensional learning model. And the neat thing about these multidimensional learning models is that there is a possibility of information spillovers where I can indirectly learn about some part of the vector that I'm trying to learn about, even if I don't directly get signals about that part of the vector. And I'll show you how the math remains tractable and clean, but that we'd need to use matrix algebra to cleanly compute a lot of the updated beliefs. So let's look at what Bayesian updating would look like if our a sub I were actually vector valued instead of a scalar. And here we're going to assume that this vector is all continuous. So we're not making a generalization to non-continuous or complicated situations that we talked about in the previous video. We're going back to the simple continuous case, but we're adding more dimensions to the learning problem. We're going to denote the vector as capital A sub I, and instead of having a variance of A, there's now going to be a covariance matrix, which we're going to call capital delta. And the signal is also going to be vector valued, so you could just think of this as I'm going to receive a 5-dimensional signal if there's 5 dimensions to A. So I'm going to have my underlying 5 dimensions of A, and then I'm going to have signals in each dimension. So the formulas for updating now, you'll see that there's some matrix inverse happening and some matrix addition. And I'll break down what these formulas are. So these are basically just vector valued analogs to those formulas I showed you a few videos ago in the scalar case. So this is basically the denominator of my variance ratio. It's just going to make it so that I put less weight on my prior if I'm more uncertain, and more weight on my prior if I'm less uncertain or more certain. And then I'm going to put more weight on my signal if I am more uncertain about my belief. So there may not be amazing intuition about these formulas, but I can just attest to you that the way they're defined, it's the vector analog of those previous formulas that I showed you. And this capital omega is a new object that we haven't really introduced. It's just a convenience object. It's a diagonal matrix with 1 over the idiosyncratic noise in that particular diagonal element. So the way this capital omega works is if I get 2 signals, I'm going to have 2 non-zero elements of omega. If I only get 1 signal, I'm going to just have 1 non-zero element. And that's going to make the math work out really nicely. And then my initial variance on A is just going to be this population covariance matrix, capital delta. And if I don't get any signals in that particular dimension of my learning, then I'm just going to set omega and S to be 0. So if I set omega and S to be 0, then I would just get ET plus 1 is equal to ET, because this would be 0, this would be 0, and then this inverse of the inverted variance would cancel with the inverted variance. And the same thing would hold here. So this is just a matrix defined system that encapsulates all of the properties that we talked about in the previous video on Bayesian updating. And the nice thing about this framework is that I could have multiple signals coming in at the same time, or I could have only 1 signal coming in each period in a different part of the vector. So now that we've kind of established that, I wanted to kind of make this simple again and go through the scalar example to kind of show how this updating actually works. So we start out in period 1 with the prior beliefs, and those are going to be the population values, because that's all the individual knows is what are the values in the population. And then they're going to get a signal in period 1 and then use that to update or revise their beliefs. And the formulas are what we talked about earlier. So in this particular setting, I've got a prior of 0 and my subjective variance belief is sigma squared A. So I'm going to hit 0 times all this is going to end up being 0, and then I'm going to have my signal times the inverted, or I guess what we would call the variance ratio. So my belief about the average in period 2 is going to be the signal times that variance ratio. And then how do I update the variance in this situation? Well, I'm just going to use that same formula, and it's going to be the product of sigma squared A times sigma squared epsilon over the total variance. And it's very easy to show that if sigma squared A is positive, then I'm going to have a lower variance in period 2 than I am in period 1. And this gets back to those fundamental Bayesian properties that we talked about in an earlier video. And then I can just repeat this over time. I can get more and more signals, and obviously the formulas are going to get a little bit more involved once I'm carrying around more terms because of the recursive structure of the formulas. But hopefully that gives you a good sense of how these things operate in reality. Let's go back to the vector example. And anywhere we saw a division on the previous slide, we're going to replace that with a matrix inversion. And then multiplication is going to be matrix multiplication. And then the other matrices like capital omega are defined just to make sure that things are conformable. And so I'm going to be able to apply these formulas to figure out what people's vector of beliefs is after receiving a signal in one particular sector. We'll go through a coding example of both of these to kind of cement your understanding of these principles, and hopefully that will be helpful to you as well. So in our next video, we'll go through a very simple unidimensional continuous learning model, and we'll follow that up with a multidimensional example. And hopefully by the end of those 2 videos, you'll have a better understanding of what is involved with these updating formulas and how to actually take this to real data. So I'll see you in the next one.